Alright guys, so we're going to continue talking about our sampling distributions, and today we're going to talk about Reese's Pieces. Alright, so suppose we have a large bag of Reese's Pieces and it has 1,000 pieces. The manufacturer says that exactly 40% of the candies are orange. If we select a sample of 50 pieces, how many will be orange? So we're going to let X equal the number of orange candies in the sample. Alright, so first off, let's think about what type of probability distribution do we have here? Let's say we can do our bins. So let's say we got our B, in which case binary, right? Success, failure. So binary, success and failure. So success is what? If we get an orange piece, right? It comes out to be orange. What's our failure? Well, if it's not orange, then we had a failure. Okay? So let's think about our I for independence, right? And with this, it doesn't state anywhere in the problem that's independent, but what we can do is do a little check here, our 10% condition, right? If I remember that, our 10% condition, in which case our sample size has to be less than 10% of the overall population. Well, in this case, we would have 50, because we said we're taking 50 pieces, and we're going to say that's less than 1/10 of 1,000, because our population of 1,000 pieces, right, that we talked about. I'm pretty sure 50 is less than that, okay? So we should check off good for independence, so independence is good. Now let's talk about our N, our sample size, right? In which case we're talking about 50 pieces. So our N, sample size, is 50. And then our S. So let's talk about our S value, okay? So the same probability, in which case it gave us that exactly 40%. So the same probability should be for all of them. So probability is 0.40. So it looks like it checks off for the bins. So we have a binomial distribution. Okay, so now let's do a little something. Let's do a simulation here. Let's take those 50 candies and we'll do this 5 times. So use a nice little applet here dealing with these Reese's Pieces, okay? So with this, I'll put the link in the description down below. And in here, I changed the number of candies to 50 because let's say we're going to take 50 just like in the problem said. And let's do it 5 times and let's see how our distribution looks. And we can animate this or not. We'll animate it, see how it plays out. All right, so we're going to the first one here to see how many orange candies come out of there. All right, first one 25. Well, that's half of 50, so let's hope it's not cheating now. All right, 21. 21 our second time. Then 25 again. So I got 25, 21, 25. Then we're going to look at seeing we've got 18. And then our last one here, let's see what it gives us. It gives us 25. So the dot plot down below there gives us a good example of that. All right, so now we've got this in our notes there a little bit what we're talking about. So with this, let's go ahead now and think about it. What does each one of those dots represent? Well, it's going to represent the number of orange from a sample of 50. So remember, each dot represents the number of orange from 50. Number of orange from a sample of 50. From a sample of 50. All right, so that's what each dot stands for, okay? Now, let's think about this. What would be the mean and the standard deviation of this distribution for the x, okay? In other words, for our orange candies. Well, with this, our mean of our x, you should remember that is n times p, in which case we had 50 times our probability, which is 0.4, which should give us 20. For our standard deviation of this, we should have square root, or n times p, times 1 minus p. So that should give us a square root of our sample size of 50. It's a probability of 0.4 times 1 minus p, which would give us 0.6, right? And this should give you 3.46. All right, that'll give you 3.46. So therefore, that's our mean and our standard deviation for this. And then now, if we were to think also about the approximate shape of the sampling distribution, how would it look? Well, hopefully you realize that it should be normal. But you're asking why? Why, Mr. Elliott? Why normal? Well, normal because of large counts. Large counts, all right? So in other words, if you have n times p, which is greater than or equal to 10, and n times 1 minus p, and that is greater than or equal to 10. So as you know, n times p, we just calculated the mean up there. That was 20. So 20 greater than or equal to 10, so that checks out. And then if we were to take 50 times 0.6, which hopefully that's still bigger than 10 as well, I believe so. And so that would give us 30, which is greater than or equal to 10. So this should check out as well. So therefore, large counts checked out. Therefore, we know that our approximate shape is going to be normal. The shape is normal. And if you were asked that, again, you would say because large counts. You can list out the large counts just as I did here. And if you put that in approximately normal and large counts and show your little check marks that those checked off, and you're all good. Now, hopefully you realize this is pretty much a review of chapter 6 that we talked about, right? So this is a complete review of chapter 6. Now let's think about if we want to do something else. Instead of finding the number of candies that are orange, let's find the proportion of candies that are orange, okay? So with this, let's see. Let's take our proportion or our values that we got from the simulator here on our orange candies. Let's turn them into proportions, right? Since these are samples, these are going to be our p-hats. Now, how do we find our sample or statistic of these samples? Well, you're going to need to divide them all by 50 in this case because we took sample size of 50. So in this case, we had 18 over 50, 21 over 50, and then we had 3 of them that were 25 over 50. So that's what we're going to do. So as I said, let's go ahead and take 18 over 50, and that should give you 0.36. And then if we took 21 was our next value, or one of our values, 20 over 50 gave us 0.42. And then, of course, we had 25 over 50. We had that 3 times. And of course, hopefully you guys can see that is 50%. So those are our probabilities. Those are p-hats, okay? These are all our p-hats for each sample, okay? Now, if we were to draw this on a dot plot, just like we had up here initially, right? Would it look any different? If we were to do this, if we were to set up saying, let's say we had, we'll go, I don't know, 0.3, 0.35, 0.4, 0.45, 0.5, 0.55. Well, 0.36, that's going to give us a dot somewhere right in here. We got 0.42, that's going to give us a dot somewhere right in here. Then we had 0.5, we had 3 of them. 1, 2, 3. Does that change anything for the original dot plot? No. The shape, quantity, and the way they're set up are all exactly the same as we did when we just did our number values. We put in proportions, the same thing, just different x values, right, or x scale. Okay, and so what does each dot represent? How is that different from above? Because each dot above represented the amount of orange candies out of 50, right? Well, these represent, each dot represents the proportion of orange from a sample of 50. So each dot represents the proportion. Okay, that's the key word right there, proportion. My P looks like a D, that's a P, proportion of orange from a sample of 50. From a sample of 50, right? So remember, be clear and state everything. So each dot represents a proportion of orange from a sample of 50. All right, so now let's go in and find the new mean and standard deviation based off of this data. Okay, so for this setup, we should be able to take our mean of the proportion, our p hat, instead of our x value was at 20, and we should be able to take that and divide it by 50. And that should give us 0.4. So 0.4 is our new mean. And for our standard deviation of our p hat, our proportions of the samples, right? For standard deviation, again, we would take the setup here for this would be the square root of 50. I'm sorry. That was a number that was going to actually write out for this. So a proportion times 1 minus a proportion over n. It's not going to be simplified, right? Well, with this, we can simply take the value that we had initially. Therefore, we had the square root of our sample size times our proportion, right, of, well, if I could write 0.4 instead of a 1, 0.4 times 0.6, we can take all that and we'll divide it by 50. And that will equal the same thing as we were to put in this calculation, right? Because in this calculation, we should get that. So this would be taking 3.46, so here's what we got, and we divided it by 50, in which case we should get 0.069. And again, if you were to put in your calculator and test it out, and you were to simply do exactly this formula right here, that will work as far as saying our proportion of 0.4 is 1 minus proportion, so 0.6 divided by our 50, all that is under the square root, you would still get 0.069, okay? So that would work out. So the new formula to understand is this one right here for the proportion, right, for standard deviation. Now, with this, would the shape or anything change for this dealing with proportions? Since we took it from our number values of the amount of oranges in a sample of 50 and put in proportions, Well, no, because of large counts, right? Large counts still works out. Large counts will still work out because we still have the 0.4 for our proportion size, right? In which case it would work out. So the large counts still works out. So large counts it is normal. Therefore, normal. All right, sorry, I did my therefore symbol a little messy. Therefore, it is normal. Okay, and again, if you're asked to draw this, it doesn't have to be anything pretty. A nice little normal curve, and then you simply need to put an N for normal, and then put your mean and standard deviation. Well, our mean was 0.4, and our standard deviation in this was 0.069 for the proportions. And you could also label this if you wanted to right here in the middle. It'd be smart to do just 0.4 so everybody knows that that's what you mean by, that's what you understand is the mean, okay? Now that we have all that, let's think about this. Since we know that those Reese's contain 40% of the pieces are orange, if we were to select a sample of 50, what would the probability be that the sample proportion will be 45% or greater? So if we wanted to find out if it would be 45% or greater, what would the probability be? So let's look at that. So again, we're wanting to see what the probability of being 45% or greater. Okay, so we want to know what the deal is with that, the probability. So we have, let's go and draw this out. Let's draw it out. I'm trying to jump too far ahead of myself here. Let's draw this out first. Again, we've got our normal curve there. Look at my beautiful curve. Isn't that awesome? All right, so again, label every time we draw a curve, and it's normal. Make sure your label is normal. So normal 0.4, and we had 0.069 for our standard deviation. Again, we'll put 0.4 right here in the middle. And then it wants to know 0.45, right? 45% or greater. So 0.45 or greater. So I want to know the shaded area under the curve for that one. Okay, so let's find a z-score. Would be the easiest way to do this. However, you can do this multiple ways in your calculator without doing that. But we'll find the z-score since most of you having to use Desmos Calculator, and we'll go through that way. Okay, so finding our z-score, we're going to take our statistic, our p-hat, minus the probability over our standard deviation in this case. So that is going to give us, again, we're looking at 0.45 is our statistic, minus our parameter of 0.4, all divided by our standard deviation of 0.069. And that you should get 0.72. So now you can do one of two things. If you have a TIN spike, you do the normal CDF. In which case, even if you label this through dealing with Desmos Calculator, you can label it that way as well. It's for easy, just constant recognition of that. And let's go and put our lower bound. So we know that this 0.45, the z-score, if we had 0 for our z-score, z-score for 0.45 is 0.72. So we're going to say our lower bound is 0.72. You have to label these so I know what you're talking about. Lower bound. Your upper bound, of course, can be positive infinity. You have to label it. Upper bound. Our mean is 0 for the z-scores. standard deviation is 1. Okay. And then we can figure out what that is. And we're going to use the Desmos Calculator to figure that out. But I'll show you in the regular TI Inspire as well. So if we're to do this on the Desmos Calculator online, go here and go to your functions, go to distributions, and we're going to do normal distribution. Again, for your mean, you can do 0, 1. Easiest way to do it. Find cumulative probability. Our minimum was 0.72, and our max is positive infinity, and just hit enter, so it automatically calculates the max. So you should get 0.2358. So you should get 0.2358. In other words, 23.58% of the time you will have, let's see, what was that? The probability that the sample portion was 40% or greater. Well, that'll happen 23.58%. Now, you can do that through the z-score, or I'll show you one other way you can do this if you didn't want to calculate z-score with these calculators, because not only can you do that with your Inspire, but through the Desmos. If you did normal CDF, you did your lower bound as 0.45, lower bound. Your upper bound is still positive infinity. Your mean, though, use the mean that you're using for those statistical values, which your mean was 0.4, and your standard deviation was 0.069. Let's see if we get the same answer. So if we did that, let's say we go functions again, normal distribution, we're going to say 0.4 for our mean, comma, 0.069, and we're going to say find a cumulative probability. Our minimum was 0.45, and oh my goodness, look at that. It is pretty much the same thing, 0.2343, so 0.2343. So we got 0.2343. So again, that's 23.43%. Both of those are correct. Either way you do that, that works out. So now if you have an Inspire, again, you can do it either way. We'll go ahead and just do it with actual numbers as well. So we're going to say menu 6, 5 for distributions, 2 for normal CDF. Our lower bound was 0.45. Our upper bound is positive infinity, a big number, so just a bunch of 9s is fine. Our mean was 0.4, and standard deviation was 0.069. Now we hit enter a couple times. As you can see, we got the same answer, 0.2343. Again, you can do it with a z-score as well. So menu 652. Our lower bound was 0.72. And our upper bound, a bunch of 9s for positive infinity. Of course, that is z-score, so leave the mean as 0 and standard deviation is 1. Click OK, and look at that, 0.2358. Same values that we got for doing it the first time through the Desmos Calculator. All right, guys, that handles everything for dealing with your proportions and idea of a sampling distribution, and I'll see you next time.